Press the accelerator pedal in many modern cars and the pedal does not mechanically pull the engine's throttle valve open. Instead, a sensor measures what the driver is requesting. Software calculates the required response. An electric actuator moves the throttle valve and another sensor checks whether the valve actually reached the commanded position. That single action contains the two ends of almost every embedded control system: sensing and actuation. A sensor converts a physical condition into information that an electronic system can use. The physical condition may be temperature, pressure, position, speed, acceleration, light, current, voltage, or chemical concentration. The sensor does not decide what the vehicle should do. It reports a measurement or a state. An actuator works in the opposite direction. It receives a controlled electrical command and uses available energy to create a physical effect. That effect may be movement, force, pressure, fluid flow, heat, light, or sound. Sensors are therefore mainly associated with system inputs, while actuators are mainly associated with system outputs. But that distinction must be understood carefully. A modern actuator may contain its own position sensor, electronics, and diagnostic functions. A smart sensor may contain signal processing and communicate through a digital interface or vehicle network. The physical device may be more complex than one simple input or output wire. Look first at what happens inside a sensor. A sensing element reacts to the physical quantity being measured. A pressure sensor may contain a diaphragm that bends as pressure changes. A position sensor may detect a changing magnetic field. An acceleration sensor may contain microscopic mechanical structures that move slightly when the vehicle accelerates. That physical change must become an electrical signal. The signal may then be amplified, filtered, temperature compensated, or converted into a digital value. The sensor's external output could be an analog voltage, an on or off state, a train of pulses, a pulse width signal, a structured digital signal, or a communication message. Software never receives pressure, temperature, or movement directly. It receives a number, voltage, time interval, counter value, or message that represents the physical condition. Engineers therefore need a defined relationship between the physical quantity and the electrical output. Suppose a pressure sensor is designed to represent its measurement range using an output from 0.5 volts to 4.5 volts. The ECU must know what physical pressure corresponds to each voltage. It may first convert the voltage into a digital count through an analog-to-digital converter, or ADC. Software then applies scaling to convert that count into an engineering value, such as kilopascals or bar. Several characteristics affect whether that value can be trusted. Range describes the minimum and maximum quantity the sensor is intended to measure. Accuracy describes how closely the reported value represents the actual value under defined conditions. Resolution describes the smallest change the measurement system can distinguish. Response time describes how quickly the output follows a physical change. Offset, noise, temperature drift, and installation conditions can also influence the measurement. This explains why reading one number is not enough for robust automotive software. The software may check whether the value is inside an electrically valid range. It may compare two redundant channels. It may compare related measurements to determine whether they are physically plausible. It may also check whether a digital message arrived on time and whether the value changes in a reasonable way. Now move to the actuator side. The ECU's microcontroller normally produces a low-power logical command. That command cannot directly supply the energy required by a motor, pump, heater, solenoid, or valve. Output driver electronics control the higher voltage or current used by the physical load. Some actuators need only two states, such as energized and de-energized. Others require proportional control. Pulse width modulation, or PWM, can control the average energy delivered to some loads by rapidly switching the output and changing the proportion of time it remains on. Motor control systems may regulate current, speed, torque, or position using more advanced power electronics. Actuators also behave differently when electrical power is removed. A spring-loaded valve may return to a defined mechanical position. Another mechanism may remain where it stopped. The required de-energized state and fault reaction are engineering decisions based on the vehicle function, system design, and safety analysis. There are two broad ways to control an actuator. In an open-loop system, software sends a command but does not directly measure the final result. For example, software may energize a simple indicator lamp and assume that illumination occurred, although electrical diagnostics might still detect some circuit failures. In a closed-loop system, a sensor measures the result and returns feedback to the controller. Software compares the commanded value with the measured value and adjusts the actuator until the error is sufficiently small or a fault is detected. Electronic throttle control demonstrates the complete closed loop. The driver presses the accelerator pedal. Pedal position sensors report the driver's request. The engine control software combines that request with operating conditions and other torque requirements. It calculates a target throttle angle. Output electronics drive an electric motor connected to the throttle valve. A throttle position sensor measures the actual valve angle and returns it to the controller. The software now has two important values: requested position and measured position. The difference between them is the control error. The controller adjusts the motor command to reduce that error. If the valve is blocked, the engine circuit fails, or the measured position disagrees with the command beyond permitted limits, the system can detect abnormal behavior and apply its defined fault strategy. Notice that the position sensor and electric motor are not interchangeable. The sensor reports where the throttle is. The motor supplies movement. The controller decides what movement should be requested. The output driver supplies controlled electrical power. Feedback closes the loop. AUTOSAR later adds software structure to these hardware paths. In AUTOSAR Classic, low-level I/O drivers handle microcontroller peripherals, while hardware abstraction layers can present hardware-independent interfaces to higher software. Depending on the ECU architecture, sensor or actuator access may also involve dedicated device drivers, ECU abstraction, or complex drivers. The exact path is project-specific, so no single simplified diagram represents every sensor and actuator. When answering an interview question, begin with energy direction. A sensor converts a physical quantity into electrical information for the controller. An actuator receives an electrical command and controlled power to create a physical effect. Then explain signal conditioning, software interpretation, output drivers, and feedback. That answer demonstrates the complete engineering chain rather than a memorized definition. Return to the accelerator pedal. The pedal sensor expresses driver intention. The controller calculates a target. The actuator moves the throttle. The position sensor verifies the result. Information travels inward, controlled energy travels outward, and feedback connects the physical world back to software. The controller coordinating all of this depends on a microcontroller that executes instructions, measures timing, and operates hardware peripherals. Lesson 4 will examine how microcontrollers are used inside vehicles and why automotive devices differ from ordinary general-purpose processors.